Okay, so in this video we're going to look at multiplication of polynomials, and just as we've done in previous videos we're going to start with conventional numbers. So let's have a look at something, let's say two-figure numbers, so let's say something like 12 times 13. Now with 12 times 13, what would we do? Well, very often we would just go for the straightforward, the standard algorithm. So we put one above the other, and then we'd multiply right to left. So 2 times 3, 2 times 1, then 1 times 3, 1 times 1, and we'd get the answer down here. We might also think of going from left to right using the expanded method, which I've argued in previous videos helps us think through exactly what's going on instead of following a process automatically. So that's another option. And a third option, which I showed you in one of the practice videos for multiplication, was Crisscross Method. And I'm going to use the Crisscross Method now because it's a useful way of thinking about how we would operate algebraically. So let's use the Crisscross Method. We would go up and down to start with. So 2 times 3 is 6. And then 2 times 1, I know that's a 10, but 2 times 1 is 2. Put the 2 underneath, and the other part of the cross, 1 times 3, 3, add the 2, that's 5. And then we've got 10 times 10 is 100, so put 1 in the hundreds column. So there's the crisscross method. The other thing that we might think about using is the grid method. And so that's when we split these numbers into tens and ones. So we have 10 plus 2, and we have 10 plus 3, and we just draw some boxes here. Whoops, I think I'll redraw that middle one. Let's see how it comes out. Okay, yeah, let's just redraw that middle one. Okay, so we have a nice neat box, and then we simply fill in all the boxes. So what we're doing is we are operating exactly the same way as we did with this crisscross method, but we're laying it out in, I guess, a kind of table. So 10 times 10 here, 100. 2 times 10, 20. 3 times 10, 30. And 2 times 3 is 6. And then we move to one side or underneath here, and we add 100 plus 20 plus 30 plus 6, giving us 156. Now this is very close to what we're going to be doing algebraically, because this, of course, is gathering like terms. So the 100 became the 1 here, the 20 and 30 are two terms which are like, so these are like terms, they became the 50, and then we have the constant of the 6, so that became the 156. I also want to mention the horizontal method where we talked about foiling, F-O-I-L, and that involved us splitting these again up into binomials. So 12 times 13 became 10 plus 2, just like in the grid method, but we put parentheses around these, and then we've got 10 plus 3. Okay? So really, these are just shorthand for these expansions here. And now we multiply out, we distribute first of all the 10 across these two terms and then the 2 across these two terms. So it becomes 10 times 10, 100, 10 times 3, 30, plus 2 times 3, so that's our 50, and then 2 times 3, 6, equals 156. So a little bit of revision there of some of the methods we use, in this case with multiplying together two-figure numbers. And that's so that when we come across here to think about the algebraic equivalent, all we're doing is replacing the idea of tens in our base 10 number system. So let's just erase the FOIL thing here, and let's write here x equals 10. So of course when we've got hundreds we've got x squared. So now instead of x equals 10 we're going to say x equals, well, anything we want to plug into it. So that's the usefulness of an algebraic expression. We can use it, it's not a fixed term, we can use it to introduce all sorts of variables and come up with formulae. But here we're just calculating out exactly the same as we did here. So instead of 10 we're going to replace with x. So now we have 12 becomes x plus 2, and we'll put that in parentheses like that, and 13 becomes x plus 3. Okay, let's just rewrite that last bracket there, keep it nice and neat. Okay, so we've got various options then for multiplying these out. Let's try a few. Let's try a column method, so x plus 2 and then x plus 3. If we used crisscross, for example, would that work in the same way? Well, let's put a line underneath. Okay, and now we've got, well, crisscross, we go up and down, then we do our crisscross, and then we go up and down again. So we've got 2 times 3, that's 6, and that goes in our constants column there. Now we've got 3x and 2x, that's our cross there, so that's 5x in our x term column there. And now we've got x times x, which is x squared. So thinking crisscross works very well indeed. Could we also use a column method? Let's try that, like the standard algorithm. Okay, so let's start with the x term here. So we've got x times 2, so that's 2x, and we have to put the 2x here. So let's put a placeholder here, plus 0. X times x, so that's x squared. And now we've got 3 times 2, so we're going to put that underneath. 3 times 2, so that's 6, plus 6. 3 times x, so that's 3x. And now we add these together. So we've got, let's go right to left, 6, add 0, well, that's just 6, so we've got a positive 6. We've got 2x plus 3x, 5x, and we've got nothing to add to the x squared, so just x squared plus 5x plus 6. So that worked quite well, although the crisscross method was rather easier, really. It's simpler. So as long as we understand why the crisscross works and that it's the same as the standard algorithm, this seems an easier way of doing it. Another method, of course, is to use the grid. Let's try that. So we've got x plus 2 and x plus 3. And then we can make a box here. Let's keep it nice and neat. Okay, like that. Okay, and vertically down. And now just fill in the box. So let's try that. X times x, x squared. X times 2, 2x. X times 3, so 3x. And positive 6 to end here. So again, adding these together, we get x squared plus 2x plus 3x. Let's just do that in one step. 5x plus 6. So again, it wasn't very slow, quite easy to do, and it's rather nice, I think, to set these out in boxes, because we can see from this graphic presentation that we should have 4 terms here, okay, because there are 4 combinations. Now let's go for the horizontal method, which we called foiling. And you'll notice that FOIL, F-O-I-L, there are 4 ways of doing this then, 4 terms, so that that's consistent with our 4 boxes here. So we go first terms, x times x, x squared. Now we do our outer terms, so x times 3, so that's plus 3x. Add our inner terms, that's 2x, gives us 5x. And our last terms plus 6. So again, very simple, very quick, and probably reliable enough. So foiling, grid method, or crisscross all seem to work very well. Standard algorithm takes a bit longer. Now, what if we had something a little bit more complicated? And let's introduce some negative terms here as well. So let's have, for example, should be able to fit it in here. Let's have x minus 2 instead of x plus 2. And now let's go for a trinomial, so a quadratic expression, x squared plus x plus 3. Keep it quite straightforward. And we'll just multiply this out horizontally. Now this time, of course, foiling, thinking just in terms of FOIL, isn't going to work because we don't just have outer and inner terms. We've got 3 terms here, and it's better to think of this in terms of the distributive law. So let's write that down, or the distributive property of multiplication. So we're going to distribute, let's put property, distributive property. So we're going to distribute both these terms in this bracket here, both these terms in this binomial, across the trinomial here, all the terms of the trinomial here. Now if we think of grid method here, how many terms should we end up with? Well, grid method helps us think about this, I think. If we have, I'll quickly sketch it down, x minus 2, and then we've got down here x squared x, so plus x plus 3, then we've got 6 boxes, okay? And vertical line down here. And so we'd fill our terms in like that. So again, horizontally, we should expect 6 terms to come out once we've distributed all of that binomial across this trinomial. So let's see if that happens. X times x squared gives us x cubed. X times x gives us positive x squared. X times 3 gives us 3x. Now we need to take care because we've got a negative term here. So negative 2 times x squared is going to give us negative 2x squared. Negative 2 times x gives us negative 2x. And negative 2 times 3, negative 6. And we did a little bit of planning here just to see how many terms we should have. So let's just check. 1, 2, 3, 4, 5, 6. So we have done exactly the same as we would have done if we'd used the grid method or if we'd used crisscross or standard algorithm or any other method. So the grid is a very useful way, I think, of thinking about how many terms should we have, and checking the number of terms is a very useful check. Okay, let's now gather like terms then. So we've only got 1x cubed, so we'll write that down first. We'll see a pattern here as well. We've only got one constant at the end here, but we do need to gather up the x squareds and the x's. So we've got x squared minus 2x squared gives us minus x squared, and we've got 3x minus 2x gives us just positive x, and finally minus 6. So there's our result. X minus 2 times x squared plus x plus 3 equals x cubed minus x squared plus x minus 6. Okay, finally, what would happen if we had, let's have 2 quadratic equations. So a quadratic equation is when you get an x squared, and it's a trinomial quadratic expression if you have an x squared, an x term, and let's say 2 at the end here, and you have a constant. So that's a trinomial. Let's have another trinomial and make it a little bit more challenging. So let's have 2x squared, so put a coefficient in front of that, And now let's have negative minus 7x, let's say, and then minus 5. Okay? So, is this going to be any more difficult? Well, we would expect, if we think about our grid here, we don't really even need to draw it out. I think we can tell that we're going to have, okay, a 3 by 3 grid. In other words, we're going to have 9 terms. So let's write 9 terms. So I think we're going to need a little bit more space than we've got here. So I'm going to put my equals sign here, and let's give it a go. Okay, so x squared times 2x squared is going to be 2x to the 4th. So x squared times an x squared gives us x to the 4th. X squared times the second term now, negative 7x. So that's going to be negative 7 times x cubed. If you like, an invisible 1 here might help you think about this. Okay, so that's minus 7x cubed. So now we've got to multiply the first term by this last term here. So we've got a negative 5 and an x squared. So that's going to be negative 5x squared. We're a third of the way through. Let's now start with this term here, the 3x. So 3x times 2x squared, that's going to give us 6x squared. 3x times minus 7x, let's put our 1 here for consistency. 3x times minus 7, well 3 times minus 7, that's minus 21, and the x times the x is going to give us x squared, so it's minus 21x squared. Okay, so then 3x times minus 5, so that's going to be minus 15x. We're 2/3 of the way through, we've just got the last term to do. So now we've just got, and it gets simpler actually as you go along because we've just got 2 here. So we've got 2 times 2x squared is going to give us 4x squared. 2 times minus 7x is going to give us minus 14x. And 2 times minus 5 gives us minus 10. Now again, good idea to do a check, because when we're working horizontally like this, it's very easy to miss one of these terms out, make a mistake. Let's see if we've got it right. So we're expecting 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's go ahead and simplify this expression. So, how many x to the 4th? Well, just 1, so we just write that one down straight away. 2x to the 4th. Now we've got x cubes. We've got 1 here, and have we got any other x cubes? Well, no, we haven't. So we can simply write. Now, is that correct? Yeah. So we simply write that down, minus 7x cubed. I'm not sure that is correct actually, is it? So if we multiplied our x squared times our minus 7x cubed, that's going to give us our x cubed there. Let's just check. What we should have done is when we had our 3x here, we multiplied it by our 2x squared. So that was here. That's a cube term as well, isn't it? So 3x. Now maybe I realized that at the time, but I didn't write it clearly. But it looks like a 2. So very easy to make mistakes here, and we need to be careful. So that's why I did that check there. I realized because of the pattern that I should have more than one x cubed. So I knew I'd made a mistake, and then it was about going back, finding the mistake, and making sure we definitely have 2 x cubes here. So we've got minus 7x plus 6x, it's minus 7x cubed plus 6x cubed, so of course it's minus x cubed. Okay, so there we go. Well, mistakes are good because every time we learn, we make a mistake, rather than feeling bad about it, we learn from our mistakes more than we learn from just doing everything correctly. So that's okay. minus 7x cubed plus 6x cubed is minus x cubed. Good, so we've recovered from that error and we move on. So now we've got our x squared there, and x squared there, and an x squared there, and that's what I was expecting. So I've got 3x squared, that sounds right. Okay, minus 5, let's just erase that. Rushing to finish, and that's not what we should be doing. We should be getting this right. Okay, so what have we got? We've got minus 5x squared minus 21x squared, so that's minus 26x squared so far, and 4, so it's going to be minus 22x squared. Okay, let's write that in. So negative 22x squared. Good, that's done the x squareds. So we need to really take care here. What have we got next? We've got our x's here, another x here, and that's what I was expecting. I was expecting it to go down again. So now I've got negative 21x, sorry, minus 15x. So easy to, lose track of where you are. So minus 15x minus 14x is going to give us minus 29x. Okay, so now finally, and then we can breathe a sigh of relief here, we've got just one term, we've got one constant, no other constants, and that's what I was expecting. It's a kind of a bell curve, isn't it, where you have one x to the fourth term, so you have one constant here, and the most frequent number of terms is these x squared terms, where we have 3 of those in the middle. Okay, so we just write down minus 10, and there's our result. So we have x squared plus 3x plus 2 times 2x squared minus 7x minus 5 gives us 2x to the fourth minus x cubed minus 22x squared minus 29x minus 10. Right, so in the second part of this video we're just going to look briefly at some quite special situations, and before we do that, just have a look at what's going on exactly as we do things like combined terms. What happens in the middle of a quadratic expression like this, for example? So what have we got here? We've got the answer to a multiplication. I'll show you what the original must have been. The original must have been x here plus 2. Okay, and here it must have been x plus 3. Okay, just bracket those off. In other words, what we have here is x plus 2 times x plus 3, giving us, let's just label them, x squared, so that's our x times our x. X times 2 gives us 2 x's, so there's one there and another one there. X times 3, so it's 3 x's, and you can see them here, x, 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 and then we've got our 6 ones here, making a rectangle. And so this is basically our grid method expressed using algebra tiles. Okay, so now if we follow this through, x times x, x squared. X times 3, that's plus 5x, x times 3, sorry, and x times 2, so we got 2x and 3x, 5x, and then 2 times 3, 6. Now, all very straightforward, but what happens if we introduce a negative? So let's use some more tiles. Okay. Now this time, we've still got our x plus 3 here, but at the top we've got x minus 2, because we've got 2 negative x's. Okay, so let's work this out. X plus 3 again times x minus 2 gives us what? X times x, x squared. So there's our x squared. X times negative 2 gives us negative 2x. So there they are, 1, 2. And now we've got positive 3x here, 1, 2, 3. And then 3 times minus 2, so that's negative 6. Okay, so when we've got a negative times a positive, these ones we have to register as negatives as well. So negative times a positive gives us negatives. So minus 1, minus 1, minus 1, minus 1, and 6 minus 1 gives us minus 6. Okay, and the reason for going through that, and something I'm sort of building up to here, is because in the middle here, something interesting starts to go on. Here, they just became added together. Okay, so we had 5x. But here, we almost get rid of the x term because we've got x squared minus 2x plus 3x is just plus x. And then we have the minus 6. Now I'm going to show you an example in a moment where that x term will entirely disappear. But just to complete what we're doing here, I want to look at the other variation on this, which is when you have two negatives. So in this case, what have we got? We've got x minus 2 again. And here we've got x minus 3. Okay. So multiplying that out, x minus 3, x minus 2. We've got x squared minus 2x minus 3x plus 6 now. So those middle terms don't cancel each other out at all. They do something rather like here. It's just adding all of these negative x's. So we've got negative x, negative x, negative x, negative x. So all of those are added together to make a negative 5x. But what we need to register here, I don't know why these are purple, but I suppose they're just like a question mark at the moment, but we need to register that these aren't negatives, they become positive because we get a minus times a minus makes a plus, or a negative times a negative makes a positive. So let's just change the colour here. So these are now, just as we had in the first example, these are positives. 1, 1, 1, 1, 1, 1 gives us 6. Okay? And let's complete this then. X squared minus 5x plus 6. Okay. But I said just now that what we're going to look at is an example where these middle terms don't just add together or nearly cancel each other out, but actually cancel each other out. Okay, so what will that look like? Well, if I show you a rather larger example, that might make things a little clearer. So now we've set up these algebra tiles, what have we got? We've got at the top 2x now, plus, these are all positives, so this is plus 5. And going down, we've got 2x again. Okay, so it's what we're doing is counting the lengths here and here, so these are x lengths. So we've got 2x again plus 5. So if we write that out, 2x plus 5 times 2x plus 5, multiply through, we've got 2x times 2x going to give us 4x squared, 2x plus 5. Well, here are these x's here or here, depending on which term we're looking at. So that's going to be plus 10x, and then the inner terms plus 10x again, and then 5 times 5, 25. And so here down here are 25 ones. And then just completing this, simplifying the middle terms here, we're adding those together, 4x squared plus 20x plus 25. Okay, so we've got 20 of these x's, we've got 25 of these ones, and we've got 4x squareds. We're going to look in a second at what happens when we've got minus 10x plus 10x. We'll do that in just a moment. But just before we do, we need to register what's going on here. What we've got here is an example of a perfect square. So the term that we use for an expression like this is perfect square. And the reason why that's a perfect square is because when we factorize it, okay, in other words, the two terms here that we multiplied together to make this, in fact, were 2x plus 5 and another 2x plus 5. And the way that we can write that is, instead of writing it out again, is we can just say squared. So 2x plus 5 times itself, if you like. 2x plus 5 times 2x plus 5 can be written 2x plus 5 squared, because that's what it is. So look out for these perfect squares. That's an example of a perfect square. And as soon as you get a perfect square, maybe given to you in a multiplication form like this, so you're told to square 2x plus 5, you should know that that simply means, and you would write it out again, 2x plus 5 times 2x plus 5. And then you can operate just as before. Okay, so that's perfect squares. Now the other example that I said we'd look at finally is when, let's see if we can change all these to, so if we change all these to negatives, then what's going to happen is these are going to be negative as well. So there we go. So now we've got, okay, minus 5, so 2x minus 5 times 2x plus 5. And we end up with minus 25 ones, negative 25. So let's write that out. So we've got this time 2, let's make it clear, put an A here and a B here. 2x plus 5, this time times 2x minus 5 gives us 4x squared, and this is where it gets interesting, minus 10x plus, there we go, plus 10x. So let's bracket those off so you can see them clearly, and then here's our minus 25. So this is the negative 25 ones here. Well, the reason why this is a special case is because what's going to happen here, I think you can see clearly, is that these are going to cancel. So these are a zero pair. You've got all of these x's here are going to disappear because they're cancelled by these negative x's here. Okay, and so you're just going to end up with these squares here. And squares is what they are, because if we now remove that middle term because it's cancelled, we end up with 4x squared minus 25. This is called the difference of example of the difference of squares. Difference of squares, and you should be able to spot these. In fact, it's really important to be able to spot these things, as we'll see later on. But just for now, so that you know the difference of squares, in terms of a multiplication, it's going to look like that. So it's going to be like we had up here, where we had the term seemingly repeated, with the only difference here that one term is positive and one is negative. Okay, so whenever we have that, if we see any term which has a positive and a negative, we know that the result of that operation is that the middle terms, the x terms here, are going to entirely disappear. And we end up with just a binomial expression. So this is a binomial result, because the middle terms have cancelled. And more than that, both of the terms in this binomial are squares, so you can see that very clearly. We've got 4x squared. If we square root 4x squared. Okay, we end up with 2x, because 2x times 2x is 4x squared. If we square root 25, then we have simply 5. So when we've got a square, subtracting another square, as we have here, then we've got a situation called the difference of squares, and that's produced by having the same expressions, but with one of those terms positive and the other negative. So that's something we're going to come across later on. It's very important, as I say, to be able to spot this and to be able to work with it. Very, very useful, interesting special case. And we've also got the example of the perfect squares where the terms are exactly the same. Okay.